Okay, good morning. Good morning. It's really our great pleasure today to have Professor SHAH with us. Professor SHAH actually needs very little introduction from me. By any count, Professor SHAH is really the top expert in the world in cement-based materials, including concrete. You can look at anything, whatever parameter. You can look at citation. You can look at the major distinguished awards that he has received. You can look at the membership of academies like US Academy of Engineering, Chinese Academy of Engineering. You can look at the research centers that he has established, the big research programs that he has established. And very importantly, he's been a great educator. So you can look at how many of his students, postdocs, and even students of his students who are like leading major research efforts in concrete around the world. Well, Professor Zhongjun Li is like a great example, of UST. And so, we talk about sustainability, right? And I think if you ask me, the sustainable achievement and contribution of Professor SHAH over many years is a great example of sustainable research, okay? And he has come up with innovations after innovations over the years, like fracture mechanics of concrete, fiber reinforced concrete, nanotechnologies, right? Damage detections, rheology. Well, the list can go on forever. But today, he's going to share with us some of his new ideas, how to sequestrate carbon in concrete. So without further ado, Professor SHAH, the floor is yours.
Okay, thank you very much, Chris. It's really nice to be here. As you know, it's been 3 years since I was here because of COVID. So it's really a pleasure. And many of you, the new people may not know, but I've been closely associated with HKUST, Institute of Advanced Studies, and Department of Civil Engineering. I came here, spent some time with Chris Lang and Zhongxing Li and other students, and it's been very, very good. And as a matter of fact, Zhongxing, one of your students who was here, Chris Ma is now, we wrote all together a proposal for ERC. It's very competitive, so you write a preliminary proposal and been selected to write a full-length proposal. So a lot of work, and it's still competitive, so it's very, very, and I like to thank the IAS organizers for arranging my visit and talk, and also Professor Chris Lang. So I want to talk about the issues with carbon sequestration. And now it's common to connect physical science with biological science. So people say, is concrete a living material? Quite often, concrete heals itself like we do. Concrete can have what we call cancer, could be the corrosion of reinforcing bar as a result of seawater, such as in Hong Kong. And concrete can breathe. And what can concrete breathe? Well, concrete can breathe CO2. And that is, in fact, subject of my talk. So we know that does this go? No. Oh, yeah. We know that CO2 emission is a big issue for many industrial processes. And if concrete can breathe CO2, then we can reduce CO2 and help with climate change. So that's what I want to talk about. How can we accelerate breathing CO2 by concrete? So that's an outline of my talk. I'm going to talk about why we need low carbon construction, conventional approach, and then I want to emphasize the new innovative approaches, some mechanism of carbon dioxide sequestration, mineralization, some commercial practice, and what materials how can we manipulate composition so we can absorb more CO2 in a shorter time. And so that's going to be essentially I'm going to talk about. I think we all know that as a result of increasing urbanization especially in developing countries, Africa and India, we will need more and more concrete and more cement. So if you look at the projection of cement production worldwide in 2050, it could be as much as 5 billion ton. That's a lot of cement. And what we want to do is that we will need more concrete, but can we do it in a sustainable way? And that's really all. Many people are working on that. We know that most of us are familiar with the concrete production has many issues like production of any material. You have a before cement production, there are pre-production such as quarrying and grinding that takes energy. After cement clinkering, we have grinding also. But the main emphasis now is so-called clinkering. So when you have a calcination of limestone, you have CO2 emission. And we want that the people say that CO2 emission during cement production could be as much as 6 to 7% of total CO2 emission. So it's a major issue, and a lot of people are working on it, on that. So there are already many successful conventional approaches to replace cement. For example, one is we all know that we use fly ash to replace cement. Fly ash is so-called pozzolanic material, reacts with calcium hydroxide and produce more good calcium silicate hydrate. However, we know that so fly ash is one, slag which comes from the steel waste product. Natural pozzolanas such as was used by Roman, and more recently clay. Clay is abundant, and when clay can be, if it's calcined, it becomes pozzolanic. And also people are talking about combining limestone and clay. I know that Professor Lang here has been working on it. So these are the conventional approaches to reduce so-called clinker content. Now, those are obviously some of them are successful, but there are some issues. For example, people say that a fly ash would be available less and less as we talk about renewable energy and use less coal for generating electricity. Some of the additives, such as large amount of fly ash, delays hydration. So I want to talk about an alternative approach to this conventional approach. And recently, people have done analysis that what are the ways to reduce CO2. So if you look at CO2 capture, so thermal energy and fuel switching during the production of clinkering is one approach. I mentioned reduction in clinker, but the large amount of now the approach is innovative technology, and they have calculated that as much as 50% of reduction of CO2 can come by using innovative technology. So what, as I mentioned, we are talking about is CO2 sequestration. So CO2 is generated not only by cement, automobiles, energy, and a whole kind of industry. So a lot of work has been done by capturing and storage CO2 underground in rock formation. We are talking about not only capturing, but using it into making it a useful product. And that's what we call, for example, carbon curing. So you have carbon curing, as I will show you, develops strength, and then it makes a useful product. So what is the breathing mechanism? So if you look at the surface of the concrete, you have a CO2 in the atmosphere, and that CO2 combined with water, you have a hydrocarbonic acid, and that combining with calcium hydroxide, we get calcium carbonate. And calcium carbonate is the one we talk about carbonation. Now, how much CO2 can be absorbed depends on many factors. I've listed here environmental factors, what's the relative humidity, how much CO2 there is in the atmosphere, temperature certainly, pressure, and how long are we going to cure it. The material plays an important role, how much water content you have, porosity obviously because CO2 is diffused, and what alternative material you can use. And that's what I'm also going to talk about. So many of you know that natural exposed concrete will absorb CO2 and we call carbonation. And in fact, carbonation is considered to be harmful, although it takes a long time. Because of carbonation, you can have a decalcification of CSH, which is not a good idea. Also, if the pH is reduced, then you have an issue with the corrosion of reinforcing bar, which is one of the major issue, for example, in the workshop that we are going to attend this weekend. Now, carbon curing is different than carbonation. You do it at very early age. The diffusion of CO2 enhances because of mineralization, makes material strong. And although initially pH value may go down, but afterwards alkalinity may be reduced. So the issues of carbon curing are different than carbonation. So there are many ways you can inject CO2. People have died during mixing or after placement, and this is what we call concrete curing, and I'm going to emphasize more, and obviously natural carbonation that I mentioned already. Already many people are working now on this CO2 sequestration, and some of them I have listed here. Perhaps one of the things more interesting is this Solidia technology, which is now also being supported by a large company called Lafarge, and they take, and I talk a little bit later on about calcium silicate and then using CO2. And there are, more and more emphasis on CO2. In fact, I don't know about Hong Kong, but here CO2 curing has become very popular. Even Bill Gates mentioned that in a CNN, that that's the way to go. Well, okay. So when you have calcium carbonate, that is, as I mentioned, CO2 and calcium hydroxide, but calcium carbonate have a different polymorphs. The most common is we call calcite, but then there is also vaterite. They are thermodynamically less stable than calcite. Similarly, aragonite and amorphous calcium carbonate. And like many amorphous material, if you can stabilize amorphous calcium carbonate, you get much, much stronger response than either calcite, valenite, aragonite. So one of my colleagues, and I don't know whether I have a slide, Varda Ashraf, she's adding, for example, biopolymer to stabilize the amorphous dopamine. Small amount of dopamine and amino acid can stabilize amorphous calcium carbonate and materials much stronger. I will show you one slide. So what are the different materials people have tried to help accelerate CO2 sequestration? Wollastonite, I mentioned, this is the company Lafarge and Solidia, and that's CAS, calcium silicate. Fly ash certainly, especially high calcium fly ash. And high calcium fly ash is not normally preferred as a pozzolanic material, but it's very good for carbonation. Red mud, I talk a bit about it. Recycled cement paste, recycled concrete aggregate, and then finally some very recent work we have done with nanomaterials. So I think there are couple of things here I want to mention. We all are familiar with calcium silicate and C2S. When we add water, we get CSH, and CSH is the one we want. With calcium silicate, such as wollastonite, If you have water, nothing happens. It's not a hydraulic material. But with CO2, you produce calcium carbonate and calcium silica gel. But there are two things here. I mean, is where really very innovations come. One, I mentioned that you can manipulate the polymorph of calcium carbonate. What is also important, but this calcium silica gel can be acting after carbonation as a pozzolanic material, which I will show you a couple of examples. So that's quite interesting. And you can control, the strength is given by both calcium carbonate and calcium silica gel, and you can control that, manipulate that, and that's a lot of research needs to be done. So I mentioned that Varda Ashraf, my colleague at UTA, is manipulating with adding, for example, dopamine. So you have amorphous calcium carbonate. So if you look at it, here is the flexural strength, and what is plotted here is total amount of poorly crystalline calcium carbonate, but here is the ratio of how much poorly crystalline calcium carbonate versus well crystalline such as calcite versus flexural strength. So you can see that the more amorphous material you have, if you can stabilize it, you can increase. So that's one direction is innovations are being done. And there are other ways you can manipulate the polymorph of calcium carbonate. Another way is, for example, here adding slag. So here you have how much CO2 you can sequester with wollastonite. I already showed you. But then if you add, and that's slag alone, because slag has a high amount of calcium. Many people are now working on MgO or magnesia. I don't know why out here. But when you combine wollastonite with magnesia, then incorporating MgO in this non-hydraulic system can also increase carbon sequestration. So these are some of the ideas. So now we talked about wollastonite. As I mentioned, it's commercialized, and how we can manipulate wollastonite to increase the amorphous fly ash. So most of the time when we use pozzolanic material, we are talking about low calcium fly ash, often people in the US call class F. High calcium fly ash is normally not preferred because of there is high CaO, calcium oxide. But for carbonation, if you have a low calcium, then calcium is used by carbonation. And as a result, you have pozzolanic reaction is less, and you have only small amount of CSH. So that's not preferred for carbonation. So for carbonation, we prefer high calcium because there is enough calcium, so you have enough calcium for both carbonation and for pozzolanic material. So that's one thing people have been. Red mud. Now red mud comes from waste material of alumina. And Professor Lee, the Zinan people tell me that Shandong has a large amount of waste red mud. And in US, in the West Coast, I mean western part of US. So what do you do with this red mud as a waste material? So this is the work done at Hunan University. And red mud has a lime, silica, and alumina. So what is done is you carbonate red mud. This is a wet carbonation, and then dry and use it as a powder. So what happens here, for example, shown, or look at the right one, calcium carbonate, how long, CO2, I don't remember, I think it was 20%, but as you, more and more time, so at about 3 hours, you have quite a bit of red mud converted into calcite. So then after 3 hours of curing of red mud, they add, I think, different amount to replace cement. So here is the red mud, 0% to 50%. Produces a compressive strength 1 day to 28 day. So you can see you have a 10% red mud to up to 20%, 28-day compressive strength compared to control goes up. The reason is that after carbonation, red mud acts as a pozzolanic material, as shown here. So you have a red mud CO2, so you have a calcium carbonate, and this amorphous aluminum silica gel. And this amorphous silica gel acts as a pozzolanic material to produce cash. So you have converted red mud is a waste material and made it into a pozzolanic material after carbonation. So you have absorbed CO2, that's a good thing. You are using waste material, which is a good thing. And obviously, there is a cost involved, but then the benefits far outweigh the cost. Now, people have been doing work, quite a bit of work also done by Prof. C.S. Poon at Hong Kong Poly, and I'm talking about his work on recycled aggregate in a minute. But let's talk about recycled cement paste. So we all know that concrete waste, whether because after the demolition or after the earthquake or after the ready-mix truck when it comes back and clean it, there is a lot of concrete we can be recycled. So currently recycled concrete aggregate is really not used for structural concrete, and the reason is that if you have a recycled concrete aggregate, when you crush it, it has this thin layer of mortar which is very porous. So it absorbs a lot of water, and as a result, when you replace natural aggregate with recycled, you can control the strength, but durability because of this weak interface is a big issue. So people are trying various ways to make recycled aggregate more like natural aggregate. What are the various ways? Well, carbonation, this is a topic of our talk, but people have used microwave to remove this layer. People have used heat treatment. People are using, for example, at IIT Madras, they are using solar energy to remove the thing. We have done work using both nanosilica, that is, if you recycle again, if you submerge in a slurry with nanosilica, the nanosilica will react with the calcium hydroxide in the porosity, and you have essentially surface which is close to natural aggregate. You can also use biomineralization, such as using bacteria. So the nanosilica work, I have done it. I'm not going to talk about it with folks at Tongji University as well as in Zhejiang with using bacteria. But what we are talking about is if you remove the cement, then you have recycled paste. If you take recycled paste and carbonate it, then you get we call carbonated recycled paste, and this is the work done with both type 1 and type C cement. So you remove the cement from recycled aggregate, carbonate it, and then it turns out that this carbonated cement paste is actually a pozzolanic material. So here if you look at the Portlandite, you take this and then along with calcium hydroxide. So calcium hydroxide and fly ash, which is a pozzolanic material, calcium hydroxide and recycled paste. So you get much more calcium carbonate, more pozzolanic than fly ash. Very, very interesting. And the mechanism is calcium carbonate plus amorphous silica gel. So then, and one more example of this. This is a work done by carbonation, work done by CS at Poly. And what no, this is continue with the cement paste. I'm sorry, this is the Hunan work. So I remember I told you that we often try to replace cement with limestone. But if you replace cement with limestone without any pozzolanic material, obviously to control you reduce the strength. But now, in addition to limestone, we have added recycled paste. And when you add recycled paste compared to the with limestone, just look at one of these. Control, addition of limestone, and limestone plus recycled paste. And you have increased compressive strength quite a bit because of the pozzolanic activity. So now the interesting work I mentioned to you, a lot of people are working in recycle aggregate. So you can work with recycle aggregate. Do we have a coarse aggregate and then very fine aggregate? Now fine aggregate work in a very interesting way for carbonation. So this is carbonation of recycled fine aggregate of different diameter, 2.5 millimeter to as small as a 0.15 millimeter. Carbonation, duration, amount of calcium carbonate, and clearly the smallest size here is the highest calcium carbonate because you have a large surface area, which is understandable. But then if you look at the smallest size and carbonated, it turns out it's a very small size, 0.15 millimeter and smaller. After carbonation, you have a calcium carbonate and silica gel. And then that acts as a pozzolanic material. So that's quite interesting. So with a coarse aggregate, you have a carbonation and it forms nice layer calcium carbonate. But with very, very fine aggregate, you have calcium carbonate as well as the silica gel, and which acts as a pozzolanic material. This is some work done in Japan, and a lot of people say you have construction waste. What do you do? Well, one way to solidify is take construction waste, whatever it is, and add a source of calcium or magnesium, and then carbonate it into solid. So you take any construction waste, let's say here, for example, they did it in just sand particles as a waste, carbonate it with the addition of calcium source, and you get a solid material. So carbonation is playing a big role in a variety of ways. Okay, so now finally I'm going to talk about nanomaterials. Now, yesterday I talked with few people, and they said, how do you get new ideas in research? So I don't know, people have different ideas, maybe Professor Lang and Zhongxin have. But I want to give you one example how I got this new idea. So let's look. I was looking at a study done at Purdue University. They have been working with nano-titanium dioxide. Many of you know that we are using nano-titanium dioxide because of its photocatalytic activity. So you get so-called self-cleaning surface. And it's available as an admixture. What they found that when they take from 0 to 2% of add to cement nano-titanium dioxide and carbonated, then what they found out that this is the addition of nanosilica and compressive strength. So up to about 1% non-carbonated, compressive strength increases, and people attribute that to the nucleation effect of hydration of nanoparticle. This has been done. But now when you carbonate it, then you can see that this is an addition of 0.1%, and you increase quite a bit the compressive strength compared to control. And if you look at the CO2 uptake, So CO2 uptake or CH consumption, so it increases up to about 1%. Now why does titanium dioxide after carbonation increase CO2 uptake? And they speculated that addition of titanium dioxide reduced the size of calcium hydroxide crystal. And if the calcium hydroxide size is crystal, they can take more carbonation. So I thought that that was a good idea, and it turns out that we have been working, as many of you know, with graphene-based materials. Carbon nanotube quite a bit, graphene oxide and graphene. And I had a postdoc, Chin Wang. She's at Beijing Civil Engineering University. And she found that when you add graphene oxide, calcium hydroxide crystal is reduced. And as a result, many of the properties, when you have a a very small amount, and I talk about it a little bit later on. So I said, if reduces the size of calcium hydroxide crystal, why not see whether it also increases the CO2 uptake? So that's how I said, okay, it's worth a try. And so that's how we started doing work on GEO. So here, for example, some work done by Chin Wang and other, where we put the size, crystal size, calcium hydroxide crystal size, you can calculate from XRD. So if you calculate, so you can see here that the addition of the GEO here in this case, 0.04%, Chin Wang had a small amount, and there is a reduction of calcium hydroxide crystal. So we decided to take GEO, and I think many of you are familiar with the graphene-based material. You have, graphene is, of course, everybody wants to use graphene, but graphene might be difficult to disperse. So you have this GEO, which is a functionalized, oxygen functionalized, and that's GEO, and it's easier to disperse, and that's CNT. I will talk a little bit. So we took GEO. This was the work done at UTU, and then we just published it, and water, and then shear mixing and ultrasonication. So you have a solution of dispersed GEO. And graphene oxide, we are talking about a very small amount, I think 0.1%. And then, of course, add cement, make a specimen, and then CO2 curing. And when you do that, so here is the compressive strength, control specimen, adding GEO, 0.05% by weight, a very small amount, and 0.1%. And as I had meant earlier, addition of GEO increases compressive strength, and one reason, there are a couple of reasons, but one was the reduction in calcium hydroxide. So after carbonation, this is control, and you can see that compressive strength increased quite a bit, addition of GEO. And same thing at 28 days. Of course, more important thing is at the earlier 7-day curing. So look at the CO2 uptake, just concentrate. So CO2 of cement paste, and when we have 0.05%, you increase CO2 uptake by 30%. That's really a substantial, and you have other benefits that we have talked about of adding graphene-based materials. And I talked about the few other additions later on. So I think that this is very interesting work, and as far as I know, the first time we showed that addition of graphene-based material can increase CO2 uptake. So that one reason, as I mentioned, is for GEO is the calcium hydroxide, but also because of this functionalization with oxygen, you notice this is also true when you mix either CNT, graphene or GEO, the layer, especially is depending upon how you are dispersing it, but if you are dispersing with superplasticizer as we are doing it, then you have the calcium ion attached to the surface, which helps in CO2 uptake. So so what is the next step? So we said that, okay, we saw that with geo. So now we want to try with carbon nanotube and cellulose nanofiber. So why carbon nanotube? Well, if you look at carbon nanotube compared to geo, has a much higher modulus compared to geo. Also, there's a higher electrical conductivity. And why are we talking about cellulose fibers? Well, they are natural, available compared to, for example, carbon nanotube. So we want to try those. That's the next direction. And I want to talk about why we are interested in see whether carbon nanotube is also can increase CO2, because addition of carbon nanotube has many other advantages. I think I've shown, we've talked this before. For example, here I've shown 0.1% carbon nanotube for concrete and measured young modulus. So here is plain concrete, young modulus is 30 gigapascal, 0.1% of carbon nanotube, and you can see you just substantially increase the modulus. And it's in many applications. I think we had done a lot of work earlier. Zhongxin had done with this for super tall building. You need to have a high modulus. And so one of the way is this carbon nanotube. We also find, for example, here again 0.1%, here is a fracture test. So plain mortar and 0.1% carbon nanofibers. So you more or less double the flexural strength. So this is why we are interested in see how CNT can do as far as this, how carbon nanotube. Also very interesting with for very high so-called high performance concrete with a low water to cement ratio, you have an issue of autogenous shrinkage. And so addition of CNT, this very small amount, 0.048%, reduces it. So with all other advantages of CNT, so we are now saying whether CNT can increase substantially, and we are also adding high calcium fly ash to really add more waste material. Then, and I think this, many of you are familiar with that, what happens with CNT at the interface. So you find out that there is more so-called high density CSH when you have this graphene-based material. So then we are also working on this waste cellulose fiber. And I mentioned this, I added this because Jishu here is working also on the natural fibers. So these are waste cellulose coming from paper industry. So and you can see, for example, his autogenous shrinkage with a control and small amount of waste cellulose fiber. Similarly here, the load versus same body curve control versus, so we want, and with the cellulose fiber, we think that it can also help with carbonation. So if you look at the natural fiber, you have this cavity. I think that yesterday I saw that here with sisal fiber. And then with CO2, you can fill up this cavity and you have a very dense material. And as you know that with natural fiber, there is an issue with respect to lignin. And normally you remove that with treatment. Here, with CO2 treatment, you don't have to worry about remove the lignin. And as a matter of fact, this is not necessarily new. There was a long time ago, many of you are familiar with cement board. Cement board is made with so-called head check process started in Australia. But in Germany, they have using wood fiber, cement, and then CO2 curing, which is the idea is the same, getting rid of the harmful effect. So I think that there are a lot of interesting things we can do with the both carbon nanotube and cellulose fiber. So I want to conclude that with some work we have been doing with biochar. And many of you are familiar with biochar. You know, you have agricultural waste. Often you burn it and it produces CO2. And actually in countries like India, that's agriculture, that's burning CO2 causes a big pollution problem. However, if you heat it so that oxygen doesn't enter, then what you come is essentially carbon, and you have a carbon negative biochar. It's a very porous material, waste material, comes from different agricultural sources. For example, in Italy, they drink a lot of coffee. So coffee bean is a source of a biochar. So now biochar, as you can see, is a very porous material. When you add it to concrete, of course, strength can go down, and there are other advantages, also like a curing agent, low thermal conductivity. But we said, how about carbon sequestration? And we want to do it clearly adding biochar without sacrificing other properties. Obviously, so we want to. So what we have been quite successful in that, and I will show you the results. So this is we have added 5% biochar, also 10% fly ash, class C fly ash, and so we have found out that the combination of 10% biochar and about, I think, I don't have the result here, but the optimal 20% fly ash gives you higher, much substantially higher CO2 sequestration and higher mechanical and other properties. So here, for example, CO2 of plain mortar, I think we have used here the CO2 concentration was 12%, and this is with 1% biochar. You almost double the CO2 sequestration. And then this is with the fly ash, then you have 100% increase because you have a high calcium fly ash. And then fly ash also is a pozzolanic activity, so you have all the other properties. So I think this is very interesting results we are just doing it. And as I mentioned, for example, mechanical, so here is a modulus, non-carbonated and carbonated, modulus with 1% biochar and modulus with biochar and fly ash. So I think that the biochar, I know that what they have done with tissue is different use of biochar, but here we are using biochar as an additional material with other properties, addition of mechanical and other self-curing, and also substantial increase in CO2. So I think that, I hope I gave you some ideas about what's happening as far as this reducing, helping climate change with absorbing CO2. And when you take the waste materials such as fly ash and recycle aggregate, red mud, so then it's really a circular economy, and that's the advantage of this kind of work. Okay, so I think that I'm going to conclude my presentation. Just to summarize, we talked about wollastonite and how we can control polymorph, fly ash, red mud, interesting, becomes pozzolanic material, the same thing with fine aggregate, and then we talked about some of the nanomaterials. So that's the end of my presentation.
Hey, Surendra, thank you very much for an excellent talk. Very insightful, stimulating as always. I just have one question. It seems that will be very good for like industrial production of products where you can have carbon dioxide. But you show that some of these companies, they're making pavements and those.
Well,
So
there
those
are
like,
now
prefabs?
people are talking about adding it during ready mix.
Oh, okay.
People are talking about adding during pumping. And pretty obviously easiest thing would be in the precast product, CO2. But I think that because of this emphasis on reduction of CO2, and now people are talking about with 3D printing. So with 3D printing, you can add CO2 before the nozzle, right, or after, depending upon how. So I think that we are just beginning to realize that this is could be a very important way to address the issue. We've all been working with replacing cement with, like you are working and others, which is also obviously important.
Yeah. Great. Any questions from the audience? Hey, Zhongjie.
Professor Lee.
Yeah, Professor Shah, you always you can do your research in the far. You see the front, you see the area. Okay, so it's very interesting to hear your current research in this the carbon. You see the. You see the cured, you see the different material. I just wondering, have you just pay attention to the concentration of the carbon dioxide, 10%, 8%, or 20%? Which one is usually the higher
concentration?
Yeah, concentration. Is the higher the concentration, the better the kiln results?
I don't think you have a good point. We are doing primarily with 12% CO2, because that is something what with the industrial emission has. But we have not, that's certainly, when you do CO2 curing, that's one, a very good point. We should see what is the effect of different, people have a higher concentration or different CO2. Very good point.
Thank you.
Yeah.
Thank you, Professor Shah. So could you elaborate more on why the carbonation can help with the decomposition of the lignin in the cellulose fiber? Is that only because of the alkalinity is reduced, or are there any other mechanisms?
So sorry, I didn't understand the question.
Yeah. So you talk about the lignin
using CO2 too.
Yes, using CO2
because they are getting rid of calcium hydroxide.
Okay.
That's it's calcium hydroxide which is the problem as far as the degradation of natural fibers. And in the to remove lignin, they use lime. High temperature lime, put the fibers and get rid of the lignin. Here with CO2, you don't have to do that. And then in addition, you are using CO2 and improving the long-term and short-term properties. But I said we had not done yet a lot of work with cellulose fiber, but we are starting.
Okay.
And I know you are working with sisal, so you might want to check.
Yeah, of course.
Why not?
That's really why
he is using a lot of, with the sisal would be the same thing.
Yeah.
We are using waste cellulose from paper industry.
I would assume probably in sisal fibers, the content of the lignin is even a little bit higher because cellulose fibers, they are totally treated, decomposed. There has been a process that they try to delignize everything here.
That's true,
so
yeah.
It could be a bigger problem for us.
Sisal fiber is a different, although they are cellulose, but composition is different than the wood cellulose fibers.
Of course. Okay. Thank you.
Okay, please. I would like some questions from students, right?
James no longer.
Next question from
He's
student.
no longer, huh?
He's with
Yeah.
the Zhongshan
Yeah.
University.
Hi, Professor Shah. Very nice to see you again. I'm Jing Yu, previously President's PhD student. Currently, I'm working in Shan Yat-sen University in Zhuhai.
You are working as a NAMI, right?
No, not NAMI. Sun Yat-sen University.
Sun Yat-sen University.
Oh,
Yeah,
okay.
in Zhuhai.
Yeah,
Yeah.
with the mask.
Yeah,
correct.
yeah.
But now I know.
Yeah,
recognize.
thank you. So thank you very much for your nice talk. Previously, you have talked about using nanomaterial to increase the carbon dioxide capture, right? So you have shown some samples, including the nano, titanium dioxide, etc. Do you think that some cheaper nanomaterials like nano carbon carbonate can also do that?
Well, yeah, that's but we don't not. It's possible, but we are talking about very, very small amount of, like, if you use CNT or GO, we are about 0.1%. So it's like adding a mixture. And the key thing is that it not only takes more CO2, but there are other advantages that many people have shown with CNT and GO and graphene, So that's the idea.
Yeah. Another question is that when we are using nanomaterials, of course, now I'm also exploring some nanomaterial in cement-based material. So when we are using nanomaterials in the concrete, the industrial guy will always ask a question, the cost effectiveness. So do you have any ideas for us to answer or to reply to them? The cost effectiveness of the using nano.
Certainly, with all of this, we have to calculate long, so-called life cycle cost analysis, including, but you have to, it's a complex issue, right? It's not only you do life cycle cost, but you have to consider other costs. For example, let's look at the aggregate. I mean, maybe recycle aggregate, you have to grind them. If you are going to do some edit, it costs money. But people don't want to quarry. I mean, that's how, people are absolutely opposed to ruin the landscape by quarrying. So all of those things have to be considered.
Yes, thank you for your sharing. Thank you.
Also social cost, right?
Yeah, social cost. We have to add that in the social consideration becomes very important. Now whenever we write an essay proposal, they insist that you include a sociologist. Yeah.
I see.
Okay.
So, Professor, I'm Hai Long Ye from the University of Hong Kong. So I have a question about the potential energy consumption and CO2 relative to the capturing of the CO2 for be used in the concrete mixing or concrete curing. So do you have any idea about the potential energy and the CO2 relative to the capturing process?
You mean how with the additional?
Yeah, additional.
No,
CO2.
that's what we have to do. Certainly, if you can get rid of, I think we are talking about getting rid of. Somebody have calculated just normal CO2 curing could account to 20% of CO2, offset 20% of CO2 generated by cement. So then, this is normal. So if you increase more CO2, and if you can say, how much you can offset with the cement production, that would be the key thing.
Yeah. The concentration of CO2 also play an important role. Yeah, thank you.
Yeah, but certainly not, it would be expensive whenever you use waste material, but then what are you, that's an additional cost, but you have to consider the whole picture.
Any questions from the students?
Okay.
Actually, one more question too. I think
we normally think that when you put carbon dioxide, it only reacts with the calcium hydroxide and turn it into some kind of a calcium carbonate. But if I understand correctly, it also somehow releases some of the silicates. Is that right?
I think that's
Yeah,
a very
that's a very
point I want to
interesting thing, yeah.
mention.
Yeah,
You
and
have
it
good
doesn't
point.
happen for normal carbonation, right?
Also, but here with the flash, if you have this silica gel, which is a beneficial.
Yes, that's
Yeah,
right.
that's
right,
I think
right.
that and so you, with the carbonation, you can manipulate the strength due to calcium carbonate as well as silica gel, and that's in a very what CS work at very fine aggregate was amazing.
Yeah.
And similarly with red mud and other issues.
Yes.
So this gives you really a new way of manipulating
Yeah.
not only the mechanical property but absorbing CO2. And with biochar, you have a start with a if you use biochar and let's say recycle aggregate, I think that you are talking about not low carbon, you are talking about negative carbon concrete.
Okay.
And that's the idea.
Very good. Yeah. Great. No more questions then. Let's thanks, Professor, again. Yeah.
Thank you.